So let's consider two types of 1-bit adders. So these are just adding single bits together, A and B. We have the half adder, and the half adder does not include a carry in bit, but the full adder does. So if we think of our, multi-bit addition, let's just do an example here, 4-bit addition. We have something here that we're adding together. So two 4-bit numbers, A 3 to 0 and B 3 to 0. And this 0th column, we're going to number these columns, column 0, column 1, column 2, and column 3. Those are the column numbers. Well, for this one, this column, column 0, we don't need to carry in. There's not a carry in on that one, so we could actually use a half adder. We may not always, as we'll show later, but in this case, there's no carry in, so 1 plus 1, 0, carry the 1. But these next columns potentially have a carry in. So this one, for example, column 1 does have a carry in of 1. And so these ones, these remaining columns, require 1-bit addition with a carry in, which is a full adder. We're going to use full adders here, and we could use, in some cases, a half adder for that rightmost bit. Okay, so let's look at the half adder to start with. And so if we add 0 and 0, so again, we're just adding these 2 bits, A and B, 0 plus 0, well, 0, for both carry out and sum. These are 2 outputs for each of those types of adders. Okay, and then we have 0 plus 1 is 1, so 1 in the sum bit and 0 in the carry out bit. 1 plus 0 also 1, and 1 plus 1 is 2, which gives us a carry out of 1 and a sum bit of 0. And then we can, write this more nicely and use sum of products, or sum of products is the easiest in this case, or K-maps, but K-maps is overkill in this case. So for C out, we get, well, that's A and B. And we could write our sum bit in sum of products form, or we just recognize it as an XOR function. Right, this would be A bar B or A B bar, right? A bar B or A B bar, and we recognize that as A XOR B. And then, as we said before, the carry out bit is just A and B. Okay, so now we have equations. We can build those from gates for our half adder. Now let's consider our full adder. With our full adder, we're going to have 3 bits that we're adding, because we potentially have this carry in bit and then A and B. And so we add those all together, carry in plus A plus B, 0 plus 0 plus 0, top row, that's 0, this is 1, this is 1, this is 2, so 1 carry out, sum is 0, 1, 2, 2, and finally 3, which gives us a carry out of 1 and also a sum bit of 1. And now written or typed. And so now we can do the same thing. And the easiest thing to do would probably be to draw this in a K-map, or recognize this as the sum function here as the 3 input XOR function, or we could write it in sum of products and then do it that way as well. So we have sum equals A XOR B XOR C in. And then we also have our carry out bit. And our carry out bit is, well, putting in the K-map is the easiest, or we can also, think about this and say, well, we're going to carry out whenever any 2 inputs is true. Okay, well, that would be A and B being true, or B and C in being true, or A and C in being true. And again, that would fall out from a K-map and putting that output in the K-map. So now we have two equations for our full adder. Required a little bit more logic. So there is a reason if we can use a half adder instead of a full adder to use that. Less hardware, less power, less cost. But we have both options, a 1-bit full adder or a 1-bit half adder. So now let's talk about multi-bit adders or carry propagate adders. So these adders propagate the carry from one column to the next. So just like we saw in our last example, we have some numbers that we're adding together, in this case 4-bit numbers. So n would be 4, 1 plus 1, 0, and then that carries the 1. So here's our carry, and that carry is going to propagate or could propagate from one column to the next. So 1 plus 1 plus 1, 3, which is 1, carry the 1. 2 is 0, carry the 1. 2 again, 0, carry the 1. And so this carry propagates from one column, or can propagate from one column to the next to the output. So here's our C out of that 4-bit adder. And so we're going to talk about different strategies for propagating this carry. So that propagation, just like when we talked about propagation delay in chapter 2, well, this propagation of the carry is going to be our slowest path. And so if we can speed up that path, we're going to speed up the whole addition. And so we'll talk about 3 different adders. The first one is the ripple carry adder, where we just basically use 1-bit adders and have the carry propagate from one column to the next. And then we talk about 2 different adders, the carry look ahead adder and the prefix adder, where we're going to speed up this slow path of that carry propagating. And so these are typically faster for larger bit widths than the ripple carry adder, but they're going to require more hardware. So we're going to pay the cost of more hardware, more power, and more actual costs, right? More money to build it. And here we have a symbol of our carry propagate adders. Again, remember all of these are carry propagate adders. It looks very similar to our 1-bit full adder, but we just increase the bit width of our inputs A and B and our sum output. So again, carry look ahead and prefix adders are faster for large adders, for larger n, but they do require more hardware.